So to help you recap, last time we talked about the regression problems. And the reason why we decided to focus on regression problems was because, in supervised learning, there are basically two different areas. One is the classification and the other is regression. And the classification problems could be represented as a regression problem, in fact, mathematically. So once you understand the principles of regression, then you'll be able to do the classification as well. So that was the motivation. Regression at the higher level, it's a prediction of a real number for a given set of features or a given set of attributes. Usually the data comes with noise, so we would hope that our model is capable of coping with the noisy data. For the notational convenience, this is going to be the notation that we'll be using to discuss our regression models. So X is a feature vector. R is a real number that we're predicting. In case of regression, R is usually in a real number space, so it can be any number, right? In case of classification, R can be a set of integers or natural numbers, which is giving an index to a certain class. And we have the superscript T to indicate the index of the data. So we assume that we have n number of data, and then T is the superscript indicating the tth data point out of those n data samples. Now, a hypothesis is a mathematical function, or it's sometimes called a machine learning model or statistical model. The hypothesis is basically a mathematical function that maps a set of features, the feature vector X, to a real value R, such that for a given data sample in a training data set, we have the prediction that correspond to the number that is associated with that feature vector in our data set. Okay, so that's our formulation. So at the end of the day, what we're trying to solve is an optimization problem where the objective is to find a hypothesis or a statistical model or a machine learning model for a given data set X that minimizes this equation over here. And if you dissect this equation, it is nothing more than just say, hey, I want the prediction result to be as close as possible to the ground truth I know. Those are the values that we already know from the training data set. I want those two to be as close as possible, okay? And as a measure of the error, I'm gonna take the square root of the difference, and then we'll take the average of that difference across all data samples. Okay, so that was a brief recap of how we, in general, formulate a regression problem. Now, one of the simplest, maybe the simplest regression model is a linear regression model where the function gx is simply just xw plus b, where w and b are the parameters that defines the shape of the function g. Okay, so the problem of finding g can be restated as a problem of finding w and b for a given data set X, and then the ground truth values R, okay? Or sometimes we call it Y. So in linear regression, the way we formulate is, first of all, we represent a set of features for a given data sample as a d-dimensional row vector, okay? And then we have a real number corresponding to that. And we can construct a feature matrix that looks like this, where each row is a row vector corresponding to the tth data sample. So as a result of that, we have a matrix. The feature matrix has a shape of n by d, where n is the number of data, d is the dimensionality of the features. We also have the a vector for the response variables. And it's basically an n-dimensional vector where each component represents the value that we're interested in predicting, right? So that's the formulation, that's the convention that we'll be using. So in the matrix representation, this was the equation that we saw last time. And then there were some, tricks that we applied to make this, addition operation disappear. And we saw that we could, by representing them like this, I found that by introducing the representation like this, we could simplify the equation in the format of y equals to ab. Okay. Now, after some derivation of the formula, we saw that the unknown, the model parameter theta, could be represented as x transpose x inverse times x transpose r. That part over here, we saw that it was called a pseudo inverse. So at the end of the day, the solution to x theta equals to r is simply just a pseudo inverse of x times r, right? And that was something that we learned from the last time. But then we also figured that there were some problems, right? So first of all, if you look at the dimension of the matrix, x is n by d dimension, which means x transpose x is going to be d by d. The inverse of d by d matrix is, d to the cube of complexity. The matrix multiplication to generate x transpose x is n times d square of computational complexity. And then as a whole, it requires, and then after that, multiplying the inverse and the x transpose to r is going to require this much of computations. So if you think about it, when you have small number of n, then this is not a big problem. We don't even care about it. You just simply calculate the pseudo inverse, and then things can be really fast. But then if you think about a situation where the number of data sample n is really large, let's say 1 million or 100 millions or even bigger than that, then computing all this is going to be quite painful. So that's the dilemma that we have in the context of big data, and that's what we covered until last week. So to this problem, we're going to talk about some of the solutions. Okay, in general, okay, in case of linear regression, it's much easier, but in general, average typical supervised learning methods are at least a complexity of n squared d squared. So again, when you have n of a few thousand, okay, 1,000, 7,000, or a few tens of thousand, it might be all right. But in case when n increases, you can see that the complexity will increase exponentially. So what can we do? There are actually several different strategies. The first strategy is sit down and cry. Okay. Well, as we will see later, I'm actually serious about the first point. Okay. This is actually a good, first strategy to try when you have a big data. Okay. I'm gonna talk about the details later. The next strategy is to somehow reduce the number of data samples or the dimensionality d. Again, the computational complexity is the function of n squared and d squared. So definitely, if you can find a way to reduce the number of n or reduce the number of d, then, well, you might be able to solve the problem in a much more efficient way. So that might be one of the strategies that you're looking for. Of course, you could also try to simplify the model. Okay, for example, linear regression model is simpler than majority of the supervised learning methods. So why not, begin with a linear regression model? Linear regression model is not that fancy. It's a straight line, right? Or in a high dimension, it's a hyperplane. It doesn't look very fancy, right? Your peers, your friends, people in your conference, in your society, they talk about deep learning and all this thing nowadays. So you have some, motivation to use deep learning and those complicated model. But I tell you, if you have big data, maybe the first thing you want to try is to actually, to apply a linear regression model, just because of the sheer complexity of the data set. Okay. We could also try to use some mathematics to make things more efficient. Okay. We could reformulate the way things are computed by applying some mathematical knowledge and then make the computation a little more efficient. So that instead of ending up using the entire, n squared, d squared order of complexity, maybe we could, for example, chop it down into smaller problems, or we can fundamentally reduce the way that, things are computed and then, reduce the computational complexity as a whole. Another strategy is to use some, big computer. Obviously, that's helpful if you can afford, especially a computer that, costs millions of dollars. Or nowadays, GPUs are quite popular and very powerful. So you can easily convert it, a gaming computer into a nice data analytics machine. And better yet, if you have a set of gaming computers, you can convert them into your own data analytics cluster. That can be really powerful. And the cost of those gaming computers are quite expensive compared to, ordinary office computers, but still way less expensive compared to, those series supercomputers. So that's, that's an amazing option. And in fact, you could actually try to apply all of the above. Okay, so these are the method that in general we'll be applying, okay, to reduce the complexity of, a machine learning problem throughout the course. Okay, so we're going to see this week an example related to linear regression problems, but down the road we're going to see a lot of strategies that belongs to either of these five. Well, actually four. You know how to cry, so I don't need to teach you how to cry. But from number 2 to number 5, we're going to see a series of solutions that belongs to either of those, four strategies. Okay. Now, when I said cry and wait, I actually meant it. I said in a sense that, well, first of all, you should kind of, pause and ponder and try to think about the problem before to jump directly into the problem. Okay, when you have big data, maybe it's better to lose a few hours or a few days for thinking about the problem than wasting several months with the computational time. Okay, so I really meant that you should really stop and cry and wait and observe what's going on with the problem. Okay, so you could, for example, let's say you have millions of data samples. Let's say you have 100 million of data samples. Begin with the simplest thing you could do. Maybe you could subsample, I don't know, 1,000, and then try to visualize them. Try to plot them in a scatter plot just to have a preliminary analysis of the, correlation between parameters and, things like that. Don't jump directly into the problem. Try to visualize their correlation, try to see if there's any tendency in the subsamples and, things like that. And once you have a clearer idea of what's really happening in a large data set, then you can start, moving ahead and seek for a computational solution to, allow you actually go over the entire 100 million data samples. Well, that's kind of an obvious thing, but, a lot of people kind of, skip that step and then just jump directly to the problem and then kind of struggle without knowing clearly what they're looking for. So I thought that was worthwhile to mention. But in terms of, technical stuff that you're going to learn from this course, of course, I'm not going to teach you how to cry. So from this slide is the real deal, right? So the first thing is to reduce the number of data points, okay? It may not always possible, but a lot of cases, it is actually possible to reduce the number of n. And this is somewhat related to clustering. So we're going to, down the semester, we're going to talk about clustering methods. And maybe you could, try to be smart and, cluster your data first, and then find a few representative samples in the neighborhood. In case you have large amount of data samples, instead of instead of fitting your machine learning model to the entire data set, let's say this is how your data is distributed. Instead of fitting your model to the entire data set, you could rather choose to find a representative example or the local average of the data set, right? And then only use those local representations to fit your machine learning model. And that might actually be more efficient while yet still giving a pretty high accuracy. Especially if your model is adaptive, then you could also try to choose a strategy where you can iteratively update your model as the stream of data comes in. So the idea is you first train a model with a small number of data, and then for the rest of the model, rest of the data set, you gradually update the model by adding samples one by one. Okay, so we're going to talk about the things like stochastic optimization and things like that in the future in this course. So those are kind of the strategies that you can apply to reduce the number of n's. Here's another thing, which is to build k number of different models and then apply the ensemble technique to come up with a model that has a good prediction accuracy on the entire data set. So basically, the idea is if you have total n data, then you could divide it into k subsets. And then for each of the k subset, you can apply, you can train a different machine learning model. And then at the end, you can ensemble them and combine them together to produce an aggregated result. So this is another trick that we're going to see, later in this semester. And finally, select a representative n in a such way that all the necessary information from the entire set, right, is captured by the subset n, right? That's, again, kind of relevant to the clustering idea, but there are systematic ways to do such a thing. And there's one thing actually that's not explicitly said in this slide, but there's also a way to split the data set into a few different chunks. And some algorithms actually allow distributed update of machine learning algorithm. So for example, maybe on Thursday, we're going to see a linear regression model being updated in a distributed fashion, okay? So that at the end of the day, we're going to compute the update at each local data set. And then the updates that are calculated at each local set is going to be applied to update the machine learning model at a global scope. So we're going to talk about this kind of trick throughout the course. It seems like there's a couple of questions coming in, so I'll try to answer them. So what is small n for slide 42? I believe slide 42 is the one that we're at right now. So the small n here is some number that we can choose, okay, to subsample the data set. So you have, let's say, 100 million data samples, and you may decide to choose to sample only 1,000. And if you sample them in a clever way, okay, I'm not going to go into the detail at the moment, but if you somehow sample it in a way that those 1,000 samples are already quite representative of the entire population, then you don't probably need, you don't probably really have to fit your model on the entire 100 million data set. Instead, it'll be sufficient to train your model on 1,000 subsamples, and that's the small n over here. Okay, so small n in the slide is the number of subsamples. Another strategy is to simplify the model. So again, linear regression, for example, xw plus b. You have only linear terms, and then you have a very small number of parameters. So why not, right? So as a matter of fact, when you have a large number of data, then my first recommendation is to begin with a simple model. Don't be a hero. Don't try to be a hero from the beginning. You need to begin with a simple model and then add more sophistication down the road as you find it necessary. If it is not necessary, if the linear model can, describe your data very well, then you don't really need to think about those complicated models, okay? Of course, you don't want to oversimplify. So in case, in fact, if you have really complicated data that is highly nonlinear, then a linear model is not going to give you a good, prediction result. That's quite obvious. But still, I still recommend you to begin with linear models. And in fact, in the middle of the semester, we're going to actually see a combination of linear models could actually be more effective than a single complicated model. So that's actually the idea of ensemble learning, okay? So you can think of a very complicated model that can, that can fit the data set at once, but you could also think of a piecewise linear approximation of data distribution. And by having a set of linear model, you might actually be able to have a better performance than a single complicated model. Of course, the efficiency is going to be much, 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 much better because you have, linear models. But yet, you might actually be able to achieve a better accuracy as a combination of linear models. So don't underestimate the capacity of linear models, okay? Because especially nowadays, that seems to be the tendency. Like everyone is using this big, gigantic hammer called deep learning, and then they're just hitting the nails around, which is understandable, right? But still, it is not always a good idea to just begin with a super complicated model and then after all realize actually the problem that you had was really simple. Strategy number four is to use mathematics. I am actually going to show you an example of how mathematics could improve the computational complexity. But, there are actually a lot of theoretical papers that uses mathematics to fundamentally change the way that the solution is computed. So for example, let's just go directly to the example. One of the popular computational tricks that's used in machine learning is what is called a singular value decomposition. So if you have taken a linear algebra class, then you probably have heard about it. So SVD is a technique, excuse me, is a technique where you're given a matrix of a size n by d, or in this figure, we're actually using m by n. So let me just follow that convention. So you have a matrix of a size m by n, and after doing singular value decomposition, you can decompose this matrix in the format of multiplication of three matrices. Okay, so the one in the middle is what is called a singular value matrix, and it's of the same size as the input. It's m by n. And then on the left and the right, we have a set of orthogonal matrices. In case you don't know what orthogonal means, orthogonal matrices, so if you have a matrix M, and if a matrix M is orthogonal, what that means is the transpose of M multiplied by M is the same as the identity matrix. Or in other words, inverse of an orthogonal matrix is a transpose of itself. Okay, so matrices that satisfy this property are called orthogonal matrices. Okay, so what the SVD says is for any given matrix, what you can do is to decompose the matrix into a orthogonal matrix multiplied by a singular matrix, and then multiply by another orthogonal matrix. And what's really interesting about this decomposition is that, well, first of all, the singular value matrix is diagonal. And what I mean by diagonal is that only non-zero values, so non-zero values of this matrix, sigma, is only at the diagonal component geometrically. Okay, so all the off-diagonal terms are zero. Only the diagonal terms have some value. Why is that important? Because one reason is the inverse of diagonal matrix is simply just the inverse of the diagonal components. Okay, which is quite easy to compute. Now, if you look at the orthogonal terms, okay, again, the inverse of an orthogonal term is basically a transpose. Now, if you think about a problem of computing the inverse, it can become actually quite simple because now we're talking about a decomposed version of the matrix where the inverse can be easily found. Okay, so that's kind of the feeling of how singular value decomposition is being used. So as a matter of fact, skipping all the mathematical details, it is known that a pseudo inverse of x, okay, which is by definition x transpose x inverse times x transpose, can actually be computed as v, which is one result of singular value decomposition, times sigma, the singular value matrix, and then times another orthogonal matrix. Well, in fact, I noticed that there's a typo in the slide. Sigma has to go to the first line. Sorry for that. But anyways, so that's what the singular value decomposition says. A pseudo inverse can be actually represented as the multiplication of the orthogonal matrices and the pseudo inverse of diagonal matrix. And like I said, the pseudo inverse of a diagonal matrix is simply just, flipping upside down for all the diagonal components. So theoretically, practically, there's not much of computational time required to compute the pseudo inverse of the orthogonal matrix. So the entire computation can become really efficient. So in fact, the exact SVD method has the complexity of this. Okay. Um, Here, notice that we have the min operator, which basically choose whichever is smaller out of these two. So in case when n is big, then the complexity of SVD is going to be d squared times n. In case when n is small, then it is likely that n squared times d is smaller than d squared n. So whichever is smaller is going to be the complexity of the exact SVD algorithm. Okay, and recall that a simple linear algebra, so that the pseudo inverse solution, the complexity of that was n squared d. So in case n is really large, then SVD might be a better solution because then the complexity becomes d squared n in case when n is really large, and therefore you can have a competitive advantage over the simple naive linear algebra solution. And of course, there are more advanced SVD algorithms that are much faster than exact SVD. Okay, so in those cases, we're talking about something even shorter than d squared n. Okay, so that's one of kind of ideas of applying mathematical principles to make the computation more efficient. Okay, so I'm not going to go too much into the details. Okay, especially I prepared a slide where it explains the SVD in a geometric sense, but I'll leave it up to you to watch this animation and try to comprehend what's going on. And this, by the way, is from Wikipedia page. So you can find actually a description associated with this animation if you Google SVD in Wikipedia. Instead, let me just jump ahead because we have a lot of things to cover. So, like what we just seen, there are many ways to actually solve that, AX equals to B problem. Okay, SVD was one example. We could also utilize some other mathematical decomposition methods such as QR decomposition, LU decomposition. In case of symmetric matrices, you can apply Cholesky decomposition, and so on and so forth. And in case you have sparse data sets, then computation can be even faster because then you can apply, for example, sparse Cholesky decomposition, which is several thousand times faster than dense Cholesky decomposition. So there are many implementation that are freely available, also commercially available. So one example is LaPeX. It's a linear algebra package written in both C++ and Fortran, I believe. I never used the other version that's C++, but LaPeX is obviously a good example. But in Python, there's also Python version of LaPeX called PyLaPeX. And there are many numerical libraries that may facilitate this linear algebra computations. In Spark also, Spark has their linear algebra library. We'll have a chance to take a look at it. But the Spark linear algebra library is also quite well optimized, and it is well suited for distributed computing. In fact, distributed computing is our next strategy. Okay, so in case you have a large amount of computational resources, then that's great. Then what you have to think now is, can we parallelize the model? Okay, so in other words, can I decompose a big problem into smaller pieces that I can distribute to different computer nodes without any dependency across those distributed tasks? Okay, so for example, if the way that you split up the problem forces you to look up the result of the other chunk's computational result. So for example, let's say you're interested in evaluating this subproblem over here, but if that evaluation has to rely on the result of the other subproblem, then that's not a good way to divide the problem. The good way to divide a problem is to get rid of any dependency across the distributed node and let the distributed nodes to compute the result independently. And then at the end, aggregate them together to consolidate a global final result. Okay, so in fact, this figure is kind of familiar to us, right? We saw at the beginning of the semester the concept of MapReduce. So if you recall, Hadoop is based upon this MapReduce computing principle, where mappers are basically a set of operations to break apart a single problem into a subproblems. And then reducers are operations to aggregate the separated computing result into a consolidated unified outcome, right? So that is nowadays one of the most popular strategies, adapted by many, big data platforms. So knowing how to do this is going to be quite important. Here are a few comments about the GPUs and things like that, but these are just for FYI. In this course, we talk about Spark and more kind of generic computing platforms. So I guess that's a little beyond what we're going to talk about in this course. So we've seen essentially 4 different strategies, right? Somehow reducing the number of data points or the dimensionality, or to use mathematics to make the problem fundamentally different, or to use a distributed computer or supercomputer. What was the other one? I forgot. Yeah, simplify the model, right? So you could either use a simple model. So in fact, in real world problem, there's no single solution. In fact, you have to try, all of the above. Okay. And, the projects that you're going to see from this class, the homework problems, is going to require to use at least, at least 2 methods. So one of the grading rubric for the semester projects are going to be to count how many different strategies have you tried, and how did you approach to a problem, and things like that. So keep that in mind, because there's no real problem where you can apply just one single method and then everything just all of the issues disappear. In fact, in reality, you need to apply a bunch of different methods as a combination. So throughout those projects, we're going to measure how good you are in terms of applying those different methods. Okay. So with that, I would like to actually move to the Colab environment. Okay, just to show you some examples of how things can be done, actually. So to get started, by the way, what I'm about to do with Colab, you don't have to actually follow all that. This is to show you and let you have a feel of how things are done, and what kind of computational improvement can be achieved by applying a different strategy. And you'll have a chance to work as a group in breakout rooms to practice all this. Okay, so for now, just try to pay attention to what I'm typing on the screen without having to follow everything. The course material, as always, is available in icon. So before to get started, here's a simple trick I show you to that allows you to measure the computational time. So for example, the Python time library is a library that allows you to check the time that is required to conduct a certain operation. So let's say here's a for loop where I have 10,000 iterations, and what I do is basically to compute the summation. Okay. So let's say you're interested in measuring the time that is required to compute this loop. Okay. A simple thing you can do is to measure the time by calling time.time method. So here then elapsed time is going to be measured as the current time. So time.time returns a timestamp at the precise moment where this line is called. Okay. So we store the timestamp right before the beginning of the for loop, right? That's the start time. And then, here we're checking the time after executing the for loop. Now, the difference between the, between the two is going to be the elapsed time, right? So simply time.time minus start time is going to give us an elapsed time, and then the unit of that is in seconds. So Here, I'm going to just print out elapsed time like this. And what's going to be returned is in seconds, how many seconds was it taken to compute these lines. So in fact, for 10,000 iterations, it took only 1 millisecond, right, to compute this, which is quite remarkable. So let's see if I can increase it any further by increasing the number of iterations to 100,000. And, simply speaking, this is a linear algorithm. So the complexity of the algorithm is going to be proportional to the number of iterations, right? So yeah, so it's roughly 10 times bigger time for this. Now, if I, let's say, have, another J loop, okay, which does technically nothing, but let's say I have this internal loop here, then executing this is going to take a lot of time, right? In fact, the computational time to execute this is going to be 1,000 times longer compared to the single for loop, because simply we're repeating this operation 1,000 times more for each of the iteration. So as you can see, from 10 milliseconds, now we move to 10 seconds to evaluate this for loops over here. So time here is a very useful and simple technique which you can use to measure the computational time required to compute something. Okay, so with that trick in mind, here what I'm going to show you is a simple simulated example of linear regression. So let's well, first off, I'm going to use NumPy in this example, just for the sake of computing the linear algebra. Now, let's say I have 100,000 data samples with the dimensionality of, I don't know, 10. Okay, so I have 10 parameters, and then we have 100,000 rows. Okay, now, since I don't have a real data, I could have used the real data, but it should be enough to use a simulated data. So I'm simply just going to create a set of random numbers. Okay, so my feature matrix X is going to be a random matrix of the average value of 0, and then the standard deviation of 1, and then the shape of the matrix is going to be n by d. Okay, so that's the usual convention that we used in the lecture slides. The response variables are going to be also, I'm just create a normal distribution. So again, the average of the distribution is 0, the standard deviation is 1, and then the size of the matrix is going to be n by 1. Okay, so again, that's exactly how things are defined in the lecture slides. Okay, so we have a bunch of random numbers. In case you're curious, we could try to just print R. And as you can see, we have some bunch of garbage numbers. Okay. Now let's think about it. To help you recall the formula, the pseudo inverse is X transpose times X, and we got to take the inverse of that, and then times X transpose. That's how you compute the pseudo inverse. Right? So that's basically how you compute the pseudo inverse. So in fact, the solution, so pseudo inverse solution of the linear regression problem is simply the pseudo inverse times R, right? That's what we've seen from the lecture slide. So here, let me clarify that the solution W is pseudo inverse times R. So what we're going to do here now is to measure the computational time required to compute the pseudo inverse solution. Okay, and here's a naive approach. I will first of all compute X transpose X. Okay, which can be done by calling np dot matrix multiplication X transpose n X. Okay, and next, obviously, the next thing to do is to compute the inverse of X transpose X. So I'm going to create a new matrix called inv, and that's going to be np dot linear algebra package dot inverse of XTX. Okay, Again, you don't have to memorize all this NumPy commands. Okay, well, later on, we'll see how this thing can be implemented in Spark. So you don't have to worry about the NumPy syntax. Now, after computing the inverse, the next thing is to multiply x transpose to the inverse, right? So that's going to be inverse times xt. So that's my variable name, which is going to be np.matmul times inv and x transpose. And finally, the solution W is the np.matmul inverse xt, right, times the response variable r. Okay, so I hope you're following the procedure here. So again, first of all, the first line computes this this line over here, this segment that I highlighted in the parentheses. So that's x transpose x, and then we compute the inverse of that. And then to the inverse, we multiply x transpose. And then finally, we have, we're multiplying r to that pseudo inverse. So that's going to be W, which is the result that we're looking for. Now, let's try to measure the computational time required to compute each of the lines. So for the first line, I'm just going to go ahead and print the elapsed time like this. Okay. The second line, we're going to try to do the same thing. So time.time, that's a timestamp right before executing this line, the inverse operation. And then I'm going to print time.time minus start time, which is going to return the elapsed time for that particular line. I'll do the same thing. And I started to be lazy, so I'm going to just copy and paste all of them, because I'm just repeating the same thing over and over. So now this is going to show me how long it takes to compute this pseudo inverse solution. And let's see, it may take some time. Well, in fact, with only 100,000 data samples, it was not that bad. So as you can see, x transpose x took about 11 milliseconds. The inverse operation has taken 4 milliseconds. And then the last one was 12 milliseconds. And sorry, the third one was 12 milliseconds. And then the last one was 3 milliseconds. So in total, it's roughly 30 milliseconds of computational time. Okay. So of course, each time I run this, depending on the current computational load on the server and things like that, the result may change quite a bit. So as you can see, as I keep running this code, the computational time is actually varying like this. So to be more rigorous, what you need to do is to take the average of multiple trials. But for the sake of this course, it's actually all right. In fact, before we move on, I would like to make a few modifications because I think it's a little too fast. So I think it is going to be sensitive to the noise. So what I'm going to do is to artificially increase the number of dimension to maybe, I don't know, 500. I hope that's not too much, but let's try. So instead of 10-dimensional feature vector, now we have 500-dimensional feature vector. Let's see how that changes. And now it takes a little longer than before. So this first line over here was roughly 1 second to compute. The inverse operation was 23 milliseconds. The third line over here was 1.6 seconds. And then the last line over here was 33 milliseconds. So, okay, that's, I think, good enough. Now, here's a little computational trick that we're going to apply. So in the naive solution, we computed this, in the order of appearance, right? So we computed everything from left to right. So to be more explicit about the way that we computed, I put a parenthesis over here, right? So we computed the x transpose x first, and then computed the inverse, and then multiplied x transpose, and then finally multiplied r. But here, what we're going to try is, let's see. So I'm going to call this an old method. And in our new method, what we're going to do is to make a slight change in terms of the order of operation that is being applied. So instead of multiplying from left to right, what I'm going to do is to multiply x transpose x and then compute the inverse. And then simultaneously, we're going to compute x transpose r, okay? And we're going to multiply this with the inverse afterwards, okay? So here's the implementation to make things more clear. So I'm going to pretty much do the same thing. Xtx equals to np dot matrix multiplication x transpose and x, okay? And then in the next line, what we're going to do is then to compute the inverse, which is np dot linear algebra library dot inverse of xtx. That's the second line. So that's the first part over here. The second part is xtr, which is np dot matmul x dot transpose and the response variable r. And then finally, the solution w is np dot matmul inverse times xtr, okay, which is the part that combines this with the next line, okay? So again, we're going to do the same thing, and I started to become lazy, so I'm going to just recycle the code that I used above, okay? So that's for the first line, and then the second line, second line, third line, and the fourth line. We should have the same set of code to measure the time. And let's see how that makes any difference. So for the comparison, previously it took 1 second over here and 22 milliseconds, 33 milliseconds. So 22 milliseconds plus 33 milliseconds is roughly 55 milliseconds. And then if you add that, then it's a little beyond the 2 seconds. And then in total, it's about, a little over 3 seconds, right? Now, let's compare that with this result over here. We have the still 1.14 seconds for computing x transpose x. So x transpose x is something that we couldn't avoid, right? So here we computed, in the old version, we computed x transpose x. Of course, in the new version, we still have x transpose x. So that's something that is, in par, right? And in fact, in the previous execution, x transpose x took only 1 second. Now here we have 1.15 seconds. So there's a little bit of penalty in the new version of the code. But still, the overall summary looks much better because, again, so the x transpose inverse is another thing that we couldn't avoid. So it's basically the same line. The only difference is the third and the fourth line, right? So if you compare the third and fourth line, in the old method, we multiplied the inverse with the x transpose first, and then computed the multiplication of r. But in the new code, we slightly changed the order of how that is computed. So we computed x transpose r first, and then computed that, multiplied that with x transpose x inverse. Now, if you look at the third line and the fourth line of the time, especially the fourth line, there's almost 0 computational burden, right? With 100,000 data rows and 500 feature vectors, still the computational speed is less than 1 millisecond, right? 0.37 millisecond is what we're talking about. So this part is almost negligible. With that being said, if you look at the third line, it's also kind of, dramatically reduced compared to what we had over here. So in the old method, we saw that it took about a little more than 3 seconds to compute the matrix W. In the new method, it took, merely a little more than 1 second, actually, right? 1.2, I guess. So it took about 1.2 seconds to evaluate this, as opposed to 3 point something seconds to evaluate this one. Okay. So what's so big deal? You may wonder, right? I mean, 3 seconds versus 1 second. I mean, it's just a 2 second difference. You may say that. Well, first of all, imagine that whenever you type a keyword in Google search, and then your web browser lets you wait for more than 3 seconds. I think you're going to be pretty angry, and you'll feel that your internet speed is so slow. The server is so slow, right? So in fact, a few seconds of difference can make a lot of differences. And plus, we're not talking about really gigantic data. It's still 100,000 samples. which is, still doable, let's say you have even greater than that, then the difference between the two methods is going to be dramatically different. Okay, so in this example, it was only 2 seconds of difference. But, first of all, it is, 3 times slower. The old method is 3 times slower than the new method, which is a big difference, in fact. And plus, second, in the real big data scenario, 100,000 is kind of a cute little number, right? It can easily go up to several hundreds of millions. So in those cases, this kind of difference in a way that fundamentally changes the computational complexity can be actually a game changer. So that's why a lot of people in this area are working on developing new mathematical methods to facilitate the computation. Okay, so again, what we've just seen was the example of linear regression. Of course, there can be many other machine learning algorithms, and in their cases, a slight change of computation can create a lot of difference, because especially in case you have a non-linear machine learning methods, then a slight change of computation is going to create a large difference. So this is going to be especially relevant if you are approaching big data problems from computer science perspective. So if you're a computer science major, your job is most likely to come up with a better algorithm, right? A better and more efficient algorithm to produce result in a faster speed. Then obviously you need to understand all this, mathematical details. But even if you're not from computer science background and just looking for, some solutions, right, for you to generate the result, it is still valuable to understand what kind of differences are there in ordinary machine learning algorithms and more advanced, more efficient computational algorithms. So I'll pause here a little bit because we have about 10 minutes, and I'm not quite sure if we'll be able to do the next topic, which is the gradient descent. The distributed gradient descent optimization algorithm. So instead of jumping into that, first of all, I would like to see if you guys have any questions or anything. And if you do, please type that on the chat. I'll try to answer them. If not, let me jump back to the lecture slide real quick. So this is essentially the same example, okay, that you just seen from the CoLab experiment. So in this case, we have a lot, bigger dimension, 1,000 dimension feature vector. And then we have 10,000 data samples. And we assume that the linear regression model looks like this. So for some reason, for the simplicity of the problem formulation, we're not using the features from X6 to X1000. Okay, that's just a wild assumption that we're making here to simplify the problem. Nonetheless, what we're going to compute is the pseudo-inverse solution. Okay, and we've just seen the Python version of implementation of that. But for those of you who are also familiar with MATLAB, or feel more comfortable with MATLAB, there's also a source code that does exactly the same thing in MATLAB. I've uploaded it on a GitHub repository, so feel free to go and check it out. But as a result of running that code, this is going to be the computational speed that you're going to achieve. So it's quite similar to what we've seen in the previous example. So we have the X transpose X, which eats up quite a bit of time. And then, the inverse times X transpose was another component that required a lot of computational time. So those two are the major contributor to the total computational time over here. Versus an improved version here, the new version. Again, the X transpose X is the same, but the later computation requires almost nothing. So as a result of that, the total computational time is much significantly smaller than the original method. Of course, you can, make it even more sophisticated by introducing some other strategies. So on top of this mathematical trick, we could also do some feature selection. So from the assumption that we simulated the situation where only 5 features out of 1,000 were correlated with the response variable. So In this case, we already know the answer, right, in terms of what we need to do to reduce the number of features. But in real problem, you obviously need to figure out a way to reduce the number of dimensionality. But at the end of the day, if you somehow successfully reduce and select the number of features, then the computational speed can, the computational time can go down even further. Okay. So in fact, we're going to talk about feature selection method later in this semester. And finally, the MATLAB code includes the simulated result of using an accelerated hardware, which in this case is a GPU. So that's particularly why I use the MATLAB code to give a demo of this, because Python is not so friendly with GPU computing unless you're using some external libraries, whereas MATLAB has all the inherent implementation of the GPU resources and everything. So here's a table comparing the GPU computation versus the CPU computation. So sorry, for some reason, some of the symbols are broken on my screen. I think it was okay on the Google slide. But anyways, what's supposed to be here is an arrow indicating that X is being uploaded to GPU and R is being uploaded to GPU. And that procedure takes 0.3 seconds. And then here, it's a process of downloading Q to the CPU core and then downloading S to the CPU memory. And that takes about 6 seconds of communication time. So, but other than that, if you simply compare X transpose X, the X transpose X itself is quite different. It's 0.7 second versus 2 milliseconds. So that's several hundred times faster, right, than the CPU result. Same thing for the X transpose R. Same thing. Well, the inverse computation was not necessarily faster, but because the inverse and inverse times S was done on the CPU. But if you look at the X transpose X, which is the major computational burden, the GPU computation is way faster compared to the CPU-based result, right? But what you have to notice from this slide is that the total computational time, ironically, is that the GPU has a larger computational time in total compared to the CPU case. That's precisely because of the data transfer time. So the way that GPUs and CPU works, at a higher level, you can consider them as different computers. The CPU has its own RAM, and then the GPU has its own RAM. So it's called a GRAM. And then originally, when you use NumPy or whatever to load the data set from a hard drive, that goes into the RAM space. And then GPU does not have a direct access to RAM. So what needs to happen is actually the variables declared on the CPU side needs to be transferred to the GPU side of the RAM. And similarly, after the computation is done, the results that are stored in the GPU side of the RAM has to be copied back to the CPU side of the RAM. So these two values highlighted in yellow are the computational time required for that communication between the GPU RAM and the CPU RAM. So in this particular example, ironically, the GPU computing is much slower than the CPU computing. However, if your problem can leverage, okay, the GPU computation, and the trade-off between the overhead for communication and the actual increase of the computational time is substantial, then GPU is going to be a better solution. So there are a couple of takeaway messages from here. So first of all, GPUs are much faster in computing simple matrix algebra. Okay, so that's first takeaway message. But the second takeaway message is that there's an overhead in terms of transferring a matrix to, from CPU side of the RAM and to the GPU side of the RAM, or vice versa, right? So, as an engineer or as a data scientist, what you need to figure out is the trade-off between, using GPUs or using, solely CPUs. So in fact, other than, people who are doing, deep learning or, other, graphics-oriented machine learning approaches, there are actually many data scientists who prefer more computing nodes on the CPU side rather than having more advanced GPUs. Okay, so it really depends on the application that you're working on. So I guess one of the main message I wanted to say over here is that GPU is not the only solution to accelerate, and GPU is not a solution that is applicable to all possible problems. Okay. And here's finally another example showing how reducing n can change the computational speed. So in this example, we just have chosen 1,000 data points and then solve the problem. And obviously, this is much faster. And in fact, if your distribution is not so nonlinear, then subsampling method is going to be as effective as using the entire data set. So with that, I'm going to wrap up today's class. And in the next lecture, which is going to be Thursday, we'll be talking about some other distributed optimization methods. And then finally, we're going to jump into Spark machine learning library, which kind of provides all this advanced techniques in a way that is very user-friendly. So thank you very much, guys, and I'll see you guys on Thursday.